Okay, yeah, this class is on the fundamental groups of topological spaces. Here we are going to discuss some additional examples of fundamental groups. So first of all, we require a definition. We want to define a concept, and that concept is about deformation retract. See, how can we define the deformation retract? For that we require a space, a topological space. Here we are going to take X as the topological space. So let us take a topological space X with a subspace. We also want what a subspace we want a subspace. That subspace here will be denoted by D. So we want a topological space, a space X, and we also want a subspace which is denoted by D. Then we will call D a deformation retract of X. We can call D a deformation retract of X provided that, see, there is a condition that is to be satisfied by the selection of the spaces X and D. What is that condition? We are coming to that condition. It is provided that there is a continuous function. There is a continuous function h. This is that continuous function. There must exist a continuous function h, which is defined from x cross I to x. H defined from x cross I to x for such that or satisfies, or that continuous function satisfies hx0. hx0, see, this is the second coordinate position 0. So when in the second coordinate position the value is 0, then and for any value of value of the point, for any point which is taken in the first coordinate position, see, the function maps to the first coordinate position, or the point in the first coordinate position, that is hx0 equal to x. In a similar way, when the second value is 1, when the second coordinate position value is 1, and then it maps to the entire subspace D. So for all x, this must happen for all x in X. For every x in X, these two conditions are satisfied. hx0 equal to x, and that means hx0 equal to x small x means a capital X. See, since this is true for all x, so you will get hx0 equal to capital X. The entire space you will get. Okay, then there will not be any change. So H will map the whole space to the same space, the entire space X to the same space when you are considering t equal to 0, and when you are considering t equal to 1, and that is the other end, the value at the other end of the interval I, you will get completely that space X is mapped to the subspace D. Okay, and the second part of the condition is that hyt equal to y. Hyt equal to y, and this is for all y in D. So when you think about a point y, which is y in D, then you can see it must satisfy, that point must satisfy the condition that hyt equal to hyt, whatever is the value of t, for all value of t, irrespective of the value of t, hyt must be same. Hyt is a constant. That means that mapping keeps the point in the subspace, all points in the subspace D, unchanged. This is that is true. Where it can keep, the mapping H can keep the points in all the points in the space D unchanged. Okay. Now we want to see some examples. So that is the procedure. Once a definition is given, we want to show that there exists some active cases that supports that example, or that proves that the example is true. So before that we have a comment. The homotopy H is called a deformation retraction. A homotopy H is here, H is a homotopy here, because it it has the property, it has the characteristics of homotopy. Then a homotopy H is called a deformation retraction. Okay, then this is called a deformation retraction. H is called because H acts as a homotopy, and it will be called the deformation retraction. And D is called the deformation retract of X. See, the subspace D is called the deformation retract of X, and the homotopy that produces, or that is behind the homotopy H, that is acting behind that the production of the deformation retract will be called the deformation retraction. Since for each y in D, for each point y in D, HYT has the constant value. See, I have mentioned that already. I have mentioned that constant value y as t varies from 0 to 1. It is sometimes said that the point of D stay fixed throughout the deformation retraction. See, the point of D stay fixed throughout the deformation retraction. Now we have examples. See, 2 or 3 examples are provided here. This example 5.1. Consider the annulus. See, annulus, the picture is provided here. By annulus we mean the space which is bounded by the 2 circles. See, you can see here 2 circles are taken with the center at the origin on R2. And this inner circle, see, this is the inner circle, and the outer circle, 2 concentric circles are actually taken, and this inner circle, you can see that it is these 2 circles make the boundary of a space. So this is the space, the annulus, which is here labeled as A. You can see A is the label given here for the annulus. Okay, and now it is clear. The space, the nature of the space is now clear, or the shape of the space is now clear. See, we can express the annulus which is given here, the space which is given here, that is A, it can be written, can be expressed mathematically as a collection of points x1, x2. See, there are 2 coordinates because it's a part of it's a subspace of R2, Euclidean 2-dimensional space. So you can represent it by 2 points. See, by a point. See, every point it can represent by that space can be represented by a collection of points having 2 coordinates. First coordinate and the second coordinate. X1 is the first coordinate, x2 is the second coordinate. It's an element of R2, provided that 1 less than or equal to x1 square plus x2 square is less than or equal to 4. Why? Because every point which belong to the annulus and the region must satisfy this inequality condition. It's because a point which is outside, see, if x is that point, and that point is marked here, and that point is that lies outside the inner circle. See, the inner circle has radius 1. Inner circle has radius 1. You can see that here the radius is 1, and the outer circle has radius 2. So if a point is outside that inner circle, which lies outside the inner circle, its distance from the distance of x from the origin. So what is the distance of x from the origin? It is the square. So the square. Okay, that distance is square root of x1 square plus x2 square. If x1, x2 is the coordinates of that point, then it is square root of x1 square plus x2 square. And so when you and that value will be less than, that value will be greater than 1. That because the radius of the inner circle is 1, so its value is greater than, the distance is greater than 1. So by squaring you get that x1 square plus x2 square. When you remove that square root, you get that x1 square plus x2 square is greater than or equal to. So this equality will be there when this point x is on the circle, when it lies on the circle. Okay. In other cases, it will be strictly greater. So x1 square plus x2 square is greater than 1. And similarly, since this point x is since it lies well inside that outer circle, having radius 2. In a similar fashion, you can show that x1 square plus x2 square is less than or equal to 4. Only that equality happening when the point is when the point comes on the circle, on the outer circle. So if the point is on the outer circle, then you get that x1 square plus x2 square equal to 4. So this is the description of a mathematical representation of that space. After that, now we will understand that the space. See, after that, we are now able to define a function that homotopy. Then we want to define a homotopy here. Okay. We can define a homotopy. Okay. I have allowed her. I have. Now this is a See, we are now able to define a homotopy. See, the homotopy H. At this moment, we are going to define a homotopy as mentioned in the definition. See, H will be defined from A cross I to S1. See, we are going to define it from the entire space, from the annulus, from the entire annulus, from this space to to its subspace, that is S1. S1, it is the inner circle. We will consider only that inner circle here as the second subspace. See, we are going to define H from A cross I to S1 by using the function, by using this expression mu of xt equal to 1 minus t into x plus t into x divided by norm of x. So norm of x is the modulus of x. By norm of x we means modulus of x. That is, in the case of this point x, it is square root of, see, norm will be square root of ordinary norm. It is square root of x1 square plus x2 square. That is the distance of that point from the origin. So once again, let's read it. Let's go through that expression, that function mu of xt, x comma t equal to 1 minus t into x plus t into x by norm of x, where x comma t is an element of, see, x comma t, this point is an element of A cross I. That means x belongs to the first space and t belongs to the second space, and that is the closed interval 0, 1. Then we have to make some verifications. We want to verify the requirements for that homotopy or the conditions of the definition. See, we want to verify that. So first one, mu of x0. Let's think about mu of x0. See, that means at the second position we are fixing 0. We are putting 0 to t equal at t, and that is t equal to 0. We put then v of x0 equal to x. It's because how do we get this? Just by substituting in this expression. In the expression, you can put t equal to 0 in this expression. But before coming to that, before going in deep into that verification, I want to mention one thing, that this function you should make by heart. This function, there is no way to develop this function yourself. So there are some many such occasions in the proof of the theorems where you want to memorize the functions. So that will be convenient when you write your examination. You cannot yourself develop that function, but if you are very if you are an expert in topology, if you have very deep understanding in the concepts in topology, then you can by taking some time you can yourself and also applying your thought process, you can develop yourself that function. But it's a fact, but from the examination point of view, that is not practical. So you should make by heart this expression. So mu of xt equal to 1 minus t into x plus t into x by norm of x is the function here, the homotopy. So when you want to verify whether the first condition is satisfied, you simply substitute t equal to 0 in this expression, and you can see that it reduces to x. And when t equal to 1 is substituted in this expression, you can see that it then produces the value x divided by norm of x, and that belongs to x by norm of x. See what happens when x is divided by norm of x. At this point you consider this point x, and when this point is divided by the distance of that point from the origin, then it will be then brought to the, it will be taken to, it will be brought, it will be mapped to the point, to the corresponding point on the inner circle when this point is joined to. See, when that point is joined to the origin by a straight line, you get a point of intersection of that line. When you draw a straight line from this point x to the origin, you will obtain a point of intersection of that line on this circle, on the inner circle. So that point is the point mentioned here. It will be then mapped to that point. That is an element of, so it's an element of S1. And also you can verify that when you take the norm of this this expression, that will be then equal to 1, and the norm of that expression will be equal to 1. Okay, therefore that condition, the second condition, is verified. Next we want to verify hyt. We want to verify hyt equal to hyt then for any value of y. So whenever y belongs to S1, so if y belongs to S1, so if y belongs to S1, then we want to verify that it's equal to S1 for all y belonging to y. It is then mapped to y, whether it is mapped to y. Okay. Okay. Then it is then HOYT now by suitably substituting y when whenever y belongs to, so for this verification we have to consider only those points which belong to S1. So if y belongs to S1, then that norm of y equal to 1. When y belongs to S1, norm of y equal to 1. And therefore when you substitute norm of y equal to 1 in this expression, so y belongs to S1 means you can substitute the quantity y, you can substitute norm of y equal to 1 in this expression. Then we get that 1 minus t into y plus t into y, it becomes, this quantity will be 1, it then reduces to y. Okay, and therefore whenever y belongs to S1, so y belongs to S1 means you get HYT equal to y. Thus H is a deformation retraction from A to the inner circle S1. And thus now that verification of the example is now complete. The verification of the example is now complete. So therefore A, the space, let's consider A x1 x2 belonging to R2 such that A square is such that A square less than or equal to x1 square plus x2 square is less than or equal to b square, and let d equal to x1 x2 an element in R2 such that x1 square plus x2 square equal to c square, where A less than or equal to c less than or equal to b, and that can also be a deformation retract. But it's the general situation, and thus see here we have verified it in the case of in the case of the example that is mentioned here, that is the case of in the case of S1, the subspace which acts as S1 which acts as the subspace of the subspace of the annulus. But you know, if we but you know, we can simply we can very easily we can extend it to a very general situation, and that general situation is provided here. It is explained here. What is that general situation? You can consider the same annulus, you know, but that annulus, but it has a radius, inner radius a, and inner circle has two circles, and inner circle has radius a and outer circle has radius b. So that is described here. The annulus is we take the general annulus a, that has inner radius a and outer radius b. But in the previous case, inner radius was 1 and outer radius was 2. So this is that space x1 x2 in R2 where a square is less than or equal to x1 square plus x2 square less than or equal to b square. Okay. And D, the deformation retract D, that can be any circle, any concentric circle, and which lies in between the inner circle and the outer circle. That can be the inner circle, either in the inner circle or the outer circle also. So that's the interesting thing. So there is a choice, a very wide choice of the subspace here in this general case. So D can be x1 x2, all the collection of the collection of all the points x1 x2 in R2 which satisfies the condition x1 square plus x2 square equal to c square, where a less than or equal to c less than or equal to b. So that also acts as the deformation retract. But in this case, you know, the deformation, that homotopy must be, that function must be redefined. See, it's the general case of that function we have defined in the previous case. So how do we define that function? hxt equal to 1 minus t into x plus hxt equal to 1 minus t into x plus t into c into x by norm of x is the function definition. So you should note that change in that function definition, and then you can verify it just as in the case of in the case of the first example. So you can verify by taking x equal to t equal to 0 and t equal to 1 separately, and then you can show the answers are obtained, the required answers are obtained, and also you can verify that for all values of t, when x belongs to that subspace that's under consideration, subspace under consideration. Okay, it is then the point is then kept fixed by this map. So that is the example. That is the general example. So the first here we have seen a simple example, and then we have explained a general example, generalized example. So the second example is now complete. Next we have to discuss some more examples, some simple examples. These are simple examples. See, the space x is a space x is contractible to a point x naught in x. A space x is contractible to a point x naught in x if and only if the single point subspace, x naught is a deformation retract of x. If and only if the single point subspace x naught is a deformation retract of x, and thus any point of any point of Rn, you consider the Rn, the space Rn, you consider the nth space, n-dimensional space Rn, any point of the n ball. When you consider the space Rn, the entire space can be can be contractible to any single point in it. So the entire space Rn can be contractible to any given point in it, and also any point of the n ball. See, any point of the n ball Bn, n-dimensional ball Bn is a deformation retract of Bn. So these are the two simple examples. Okay, by this we can stop this video now. Okay, thank you for listening.